Alright, today we're going to have a look at titration calculations. Okay, that's what we're going to begin with. As well, we're going to look at pH levels. Okay, so how titration calculations work is that we want to calculate an unknown concentration, right? Either of an acid or either of a base. Okay, and it follows a general equation, all right, of a normal acid-base reaction. So you have an acid plus a base, you get a salt plus water. Okay, that's what happens. Notice you'll see letters there such as A and B. What are A and B there for? A and B are the balancing numbers, because as we know that all equations must be balanced. Okay, now at equilibrium or at equivalence point, what's going to happen is that the number of moles used of your acid, which is Na, is equal to the number of moles of base that is used. In other words, they are in the same proportion at equivalence or at endpoint. Okay, so we know that we need to find the concentration, and we know how to find concentration if we know what is the number of moles as well as the volume. We use N is equal to Ca Va. Now that's for the acid. Okay, and then for the base it'll be the same formula but just of the base. So Nb is equal to Cb times Vb. If that is the case, all right, in other words, they are in the same proportion. If that is the case, then that means Ca times Va, the concentration of the acid multiplied by the volume of the acid, divided by the concentration of the base multiplied by the volume of the base, is equal to the number of moles of the acid divided by the number of moles of the base, which is equal to A over B. Okay, and that's essentially how titration calculations work. We're going to have a look at it in a real live example in just a momento. Okay, so over here, I wrote the question further up over here. We have a situation where we have 22 grams of washing soda, all right, which is dissolved in 220 milliliters of H2O, in other words, water. Calculate the concentration of the solution. Now that is quite basic, of course, am I correct? And I'm actually going to leave that example up to you all to do before I do it. So if you can all just find the concentration of this washing soda, which is Na2CO3, you can please find that concentration for me. I would be delighted. So with that little example there, so that was a question that was setting you up for a titration question, which is in 2 point, which is in the second question B. But for A though, okay, we know the concentration formula, which is our first step. C is equal to N divided by V. Okay, so we know that we have mass, which is 22 grams, and we also have volume, which was 220 milliliters, 220 milliliters, which we need to convert to decimeters cubed. Okay, so 220, we divide that by 1000, we should get 0.22, so we get 0.22 decimeters cubed for our volume. Okay, so we have a slight little problem here which we can solve very easily, of course. Is that we know that C is equal to N times V, N over V, but N, number of moles, is equal to the mass divided by the molar mass. We can merge these two formulae together to form a new concentration formula, which is C is equal to M divided by molar mass times the volume. So we can do 2 in 1. Yeah, you substitute in 22 for the mass divided by the molar mass. So we know that washing soda All right, which I'm going to do also on this side, is Na2CO3. So the molar mass for that would be 2 times 23. Okay, because 23 is the molar mass of sodium, plus carbon, which is 12, plus 3 times 16 for oxygen, and we should get a value of 106 grams per mole. 106 grams per mole. There we go. So substitute that in. 106 grams per mole multiplied by 0.2. Okay. Therefore, we punch this all in on our calculator. We got 22, and we got 106 times 0.22. And we get a concentration of, rounded off to 2 decimal places, of 0.94 mole per decimeter cube. Right, so we want to have a look at the solution to the second question, B, and we're going to go with the first question, which was write a balanced equation for it. Now, in the question, I gave you the molecular formula of washing soda, Na2 CO3, alright, and it reacted with a solution of sulfuric acid, H2SO4, and what was the products? Let's see. Well, a salt forms, and the salt that forms is Na2SO4, and we know because of the presence of a carbonate in the base reacting with the acid, we know the byproducts that are going to be formed is H2O, which is water, plus carbon dioxide, CO2. Wonderful. Having a look at the second question. The second question asked us to calculate the concentration of the acid. In this case, it was sulfuric acid. So the formula for titration, we have CaVa, which is concentration of our acid divided by the volume of our acid, and or times the volume of our acid, sorry, divided by the concentration of our base times the volume of our base, which should be equal to the number of moles of our acid divided by the number of moles of our base in B. Alright, so we can go ahead and substitute what we know. Alright, so if I just go check the question again, they told me I had 20 cubic centimeters of washing soda. 20 cubic centimeters. So if I have to convert that to, decimeters cube. So if I go do that quickly over here, concentration of, let me just check something. Yes, concentration of my base I just calculated to be 0.94 in the previous question, multiplied by the volume, which was 20 cubic centimeters, which if I divide by 1,000, I get 0.02 decimeters. The concentration of my acid is what I don't know, but it did say in the question that 20 cubic centimeters of washing soda solution was used to neutralize 32 centimeters cubed of sulfuric acid. So we know that Ca must be multiplied by 32, so I need to divide that also by 1000 to get that to decimeters cubed. 0.032 decimeters cubed. Now remember, the formula is equal to Na over Nb, which is equal to your A over B, and A over B we knew was our balancing numbers. Alright, in other words, the mole ratio. And you can see everything is balanced in the ratio of 1:1. 1:1:1, so they are all balanced. So therefore, it's just equal to 1/1. Alright, I'm going to explain that again, because everything is in proportion of 1:1:1:1:1:1. Okay, So therefore, CAVA divided by CB, VB is equal to N of A, NA divided by NB is equal to A over B. In this case, 1 is over 1. Hope we all grasp that. Okay? What we do next is that we put this on the top stays the same. Okay, we just find a value for what's our denominator at the bottom. So 0.94 multiplied by 0.02. Okay, we get a value of 0.0188. So we end up with 0.032 Ca, which was divided by the answer we get at the bottom, 0.0188, which is equal to, well, 1 over 1 is 1. Take it over to the other side by multiplying this side by 0.0188. We do the same to that side. We end up with 0.032 Ca is equal to 0.0188. Divide both sides by 0.032, and therefore we scroll down a little bit, the concentration of the acid that we should get, which is H2SO4. Alright, we just divide it by 0.032, 0.5875, so we can round that up to 2 decimal places to be 0.59 mole per decimeter cubed. Third question said, now determine the pH range at the end point. And I'm going to do this solution over here. Right, so the pH range. Now the value that we got though for our Ca, which I'm just going to rewrite over here, was 0.59 mole per decimeters cubed. And they said determine the pH range. Okay, now we can clearly see that this is an acidic solution, more or less. Alright, and we know that H2SO4 is a strong acid. Alright, in the list of acids according to strength, which I did with you guys about 2 weeks ago, we know that there was a list, and H2SO4 was quite higher on the list because it's quite a strong acid. And then in the list of bases that I gave you as well, we had Na2CO3, and that was considered to be quite a weak base. So we actually had a reaction where a strong acid was reacting with a weak base. Cool. So if a strong acid reacts with a weak base, okay, the stronger the acid, the lower the pH level will be. Okay, now we know the pH level. Alright, if the pH is equal to 7, we know that this means it's neutral. Alright, so anything to the left of 7 is going to be considered a lower pH. Anything to the right of 7, alright, is going to be considered a higher pH level. Okay, of course. So we have 0.59 as our concentration, and we had a strong acid reacting with a weak base, meaning that it's leaning more to being an acidic solution, meaning that therefore, for the third question, the pH range, alright, is basically, well, let me write it full out, pH range is less than 7 because it is more acidic. Strong acid H2SO4 reacting with a weak base, reaction is more acidic. So we can say strong acid, comma, weak base. If it had been the other way around, if it had been strong base and a weak acid reacting with each other, the solution would have been more basic, resulting in a higher pH level or higher pH range. The auto-ionization of water, basically what this is saying is that pure water, alright, ionizes to a small degree. Alright, the H2 molecules that are in contact with each other, they do undergo a process which is named there for you called auto-ionization. Okay, now we all know from the beginning of the section that water is amphiolite, meaning it can act as an acid or base. When water or pure water rather, auto-ionizes, basically some water molecules, H2O molecules, they do act as an acid, donating a proton, which is your hydrogen plus ions, and some actually act as a base, which means they actually accept the hydrogen plus protons. Okay, and the equation that you see there is when water, H2O liquid, reacts with water, H2O liquid, we see hydronium ions formed, H3O plus hydroxide. Alright? And basically, how this happens is that the equilibrium is very far to the left because very few water molecules actually form ions. Alright, when water is in its purest form. So how the bottom arrow must actually exist is it mustn't be the same length, but if equilibrium is going to be leaning more towards the left hand side, because the degree to which water ionizes in its pure form is quite small. Alright, so it leans more towards the left and not to the ion side of the equation. You'll notice also on the screen the equilibrium constant, or otherwise known as the ionization constant for water, is given as Kw. Okay, W for water. Basically, we are taking, oh, I'm missing out something, sorry, that's what I was looking at. Needs to be squared there because there's two waters. Products over our reactants, okay, but the concentration of our products divided by the concentration of our reactants, okay, which is the same for the equilibrium constants Kc, which we learnt in the previous section. Okay, so water follows a general equation, H3O plus, the concentration of H3O plus, multiplied by the concentration of hydroxide, OH minus, divided by the square of the concentration of water, which is H2O, of course. Okay, now H2O, the concentration of water, is a constant and is incorporated into the value for Kw, so we end up with just the top part, which is H3O plus multiplied by OH minus, square brackets for concentration. We get 1 times 10 to the negative 14 as the auto-ionization constant of water. Notice I have inserted a very key component there, which is 25 degrees Celsius. This value, this constant of water, only exists at 25 degrees Celsius. It does not exist when the temperature is higher. If it's higher, okay, at a higher temperature, then that means Kw will be higher. But most often than not, for your scholar purposes here in grade 12, water will always be assumed to be at this degree Celsius unless they give you a value for Kw, saying the value for Kw is a certain number. Obviously, if it's higher than 1 times 10 to the negative 14, you know it is at a higher temperature. So this is a constant. You'll never be asked to, or you should never be asked to show this, but it's a constant, okay? So this is just for learning purposes. But in the same way, we can calculate the ionization constant of acids as well as bases, okay? Which I'm going to show you on the next layer. Okay, now when acids dissolve in water, they follow a general equation. Okay, I'm just going to get my colors sorted out. There we go. They follow a general equation, which is HA. So H is your hydrogen bonded to your acid. Okay, acids contain hydrogen in them. Okay, your hydrogen or your acid, HA, A for acid in aqueous solution, plus water, Okay, what does it give us? It gives us H3O plus in aqueous solution plus A minus. In other words, this is the substance that is left after the acid has donated the proton. Okay, so example of that, we have HCl, hydrochloric acid, in aqueous solution plus water, which is our liquid. Okay, and we end up with still H3O plus, which is in aqueous solution, plus what is left after the hydrogen has been donated to water. We just left with Cl minus, also in aqueous solution. Okay, so the same acid and base reaction that we know oh so well. Okay, same thing. All right. The same thing goes that we bases dissolve in water. Okay. Similarly, sorry, I shouldn't say same thing, but similarly, where bases dissolve in water, right? We have B, which is our base. This is the general equation. Plus water, we end up with the base that has accepted the hydrogen proton. So we have BH plus our hydroxide, which is OH minus. An example of that, if we have ammonia, NH3, okay, if we have liquid ammonia, we add that or react that with water. Remember what we said, water is an amphiolite. So in this case, because this is our base, all right, this is our base, all right, our water, it will act as an acid here, meaning that it will donate a hydrogen to NH3, which will take that to ammonium NH4 plus in aqueous solution, plus our hydroxide OH minus, also in aqueous solution. Okay, so before we get to the Ka and Kb, the ionization constants of acids and bases, you must understand that this is what happens when bases as well as acids dissolve and ionize in water. So these are the general formulae of the ionization constant of an acid with a and this is the general formula for also the ionization constant of base. So for example, I'll do the base first because my color is in blue. For the reaction that we just had, okay, we had ammonia NH3 plus water, which gave us NH4 plus in aqueous solution, plus hydroxide, which was OH minus in aqueous solution. These are always our products over our reactants. In this case, it's our products divided by our concentration of our base. So what we end up with is the ionization constant of our base, which in this case was NH3. Right, we have NH4 plus, the concentration. Okay, there's no values for this, I'm just subbing in from what I know. And OH minus will always be there because it's from the general equation, and our base, it was obviously NH3. Okay, and then if this was a real question and there was values, you just sub in. But for our acid, right, with the example that we had with our acid, we had HCl plus H2O, which gave us H3O plus in aqueous solution plus Cl minus. Okay, what we do then is now we have the K, or the ionization constant of HCl. Right, we sub that in there, equals to our concentration of hydronium H3 plus, multiply by Cl minus ion, all divided by the concentration of hydrochloric acid. Right. and that's what we get. Now, keep in mind that these are constants, Ka as well as Kb. They are constants. In other words, there's only values for them. Okay, they do not require units, of course. This does not exist for strong bases, for example, right? So this one wouldn't exist for a strong base, okay? Because strong bases, they dissociate completely in water, all right? So if we had a strong base such as sodium hydroxide, okay, let's take a strong base. So if we have NaOH, which is a very strong base, okay, and you react that with water, it dissociates completely into sodium and hydroxide ions. So you end up with Na plus in aqueous solution plus OH minus also in aqueous solution. So we cannot obviously perform a ionization constant calculation for a base such as NaOH, sodium hydroxide, because it's very strong and it dissociates completely in water. The next thing I want to touch on for this session as well is called the pH scale, right, or pH levels. Okay, as we've seen already, we've already briefly been touching on pH scale, but what we have discussed about it, what we do know about it, is that it is a scale that ranges from values between 1 to 14. Okay, and the pH scale exists to showcase or indicate the degree of acidity. Okay, it's used to indicate the degree of acidity. In other words, how acidic is the substance. Okay, so the concentration of H3 plus in a solution, that is used to calculate the pH value, okay, of a solution. All right, so this part, H3O plus, the concentration of it, which is obviously in moles per decimeters cube, is a very key component of determining just how acidic a solution is. Okay, it's a very small value often, okay, and that's the reason why chemists developed the pH scale. Okay, and the pH scale uses a negative logarithm of the hydronium ion concentration. Okay, so the pH scale follows this formula, which is negative log of the concentration H3O plus, which is the hydronium ion. Okay, so this exists for acids. Okay, base has its own one, which is the pOH level. Okay, which is similar, except that we're now no longer taking the negative log of the hydronium ion, but rather of the hydroxide ion. Alright, we're taking the negative logarithm of the hydroxide ion concentration to determine no longer the acidity, but the alkalinity. Alright, just how alkalinic, how much of an alkali it actually is. But focus on the pH scale, the pH level for an acidic solution. Okay, for an acidic solution, okay, the pH level will be greater than 1 times 10 to the negative 7. All right, example 10 to the negative 3. If you get a value that's got 10 to the minus 3, we know that it is very acidic. Alright? It's very acidic. Okay? And or basically it's to the left of 7, because a neutral solution, alright, is going to be 1 times 10 to the negative 7. Okay? That's how we know it's neutral. Alright? 10 to the negative 3 is obviously to the left. Alright, in other words, the pH scale, let me just get this value here. In other words, on the pH scale, the pH is going to be less than 7. Okay, that is your for your acid solution. So for example, if I take a look at the pH, if I negative log 10 to the minus 3, you can put this on your calculator if you want to as well, I'll get negative of negative 3. Okay, this is log rules, and I'll get a value of 3. If I negative log 1 times 10 to the minus 7, or just negative log 10 to the minus 7, I get obviously negative times negative 7, which gives me a pH level of 7. I know it's neutral. Okay, but for alkali, we also know the pH is going to be greater than that of 7. Okay, so 1 times 10 to the minus 7. And example, we have 10 to the minus 11. Okay, which is obviously greater than 10 to the minus 7, of course. So minus log concentration 10 to the minus 7. You see, sorry, let me just change that bracket there in the beginning here. 10 to the minus 11, sorry. Alright, what we're going to get equals to is minus 11. It will give us answer of 11. 11 is greater than 7. We know it's an alkali. If it's 7, we know it's neutral. And if it's acidic, we know it is less than 7. Okay, what I should probably also do is just switch these signs around, because see, they are a little bit funky. Put it back here. Why is it not working? There we go. There we go, and move that way, and here we go. Awesome. These are your 3 types of acids that exist. Okay, we know that a monoprotic acid, we know that 1 mole of acid produces 1 mole of H plus ions, which basically means that the concentration of 1 H3O plus, okay, basically is equal to the concentration of the acid. But with diprotic, we know that there's 2 moles, or 1 mole of acid produces 2 moles of H plus ions. In other words, it has 2 hydrogen proton ions, H plus ions to donate, which means that 1 mole of H3O plus basically is 2 times the concentration of the acid, and I'll show you guys that in an example. And then for triprotic, it obviously means exactly the same thing, except it's no longer twice or 2 times the concentration of the acid, but 3 times the concentration of an acid. And to show you that in an example, okay, if I have H2SO4, okay, H2SO4 solution, okay, and I have a concentration of 0,025 mole per decimeter cubed. Okay, and the question that I need to do is calculate the pH level. Well, this part over here saying that 1 mole of H3O plus produces 2 moles of hydrogen or H plus ions, which means that's how I start my formula out. So basically the concentration of H3O plus, okay, therefore, equals 2 times my acid, which is what? H2SO4. H2SO4. Okay, now they gave me that concentration, right? So the concentration was 0,025, so 2 times 0,025 should give me a value of 0,05 mole per decimeter cubed. Okay, now that's not obviously my final answer. They want me to calculate the pH. Well, the pH level must be equal to minus or negative log of the concentration of the hydronium ions. Okay, in this case I just calculated because my formula said that the concentration of the hydronium ion must be twice that of the concentration of the acid. So I substitute this because therefore the concentration of H3O plus was equal to 0.05. Right? So minus or negative log 0.05. Alright, I put that in my calculator, and therefore the pH level that I get for a H2SO4 solution with a concentration of 0.025 mole per decimeter cubed to equal 1.3 or 1.30. Right? It is a pH scale. It is just a value, just no units. So 1.30 means that it is got a pH level of basically 1. Alright, because it's very much close to 1, and that does back up the fact that H2SO4 is a strong acid considering how far away from 7 it is. I want to apologize, grade 12s. My signs were correct to begin with in the beginning. Basically, this is the concentration. So if your concentration is greater than 1 times 10 to the minus 7, so 1 times 10 to the minus 3 is greater than 1 times 10 to the minus 7, of course. As we know, negative 3 is bigger than negative 7, alright, because negative 3 is closer to 0. That's how the negative number line works. Numbers on the left hand side of 0 work. The closer you get to 0, so negative 1 is obviously greater than negative 2. So my signs were correct. If my concentration is bigger than 1 times 10 to the minus 7, it's an acidic solution. My pH level though will be less than 7. Okay, and for alkali, if my concentration is smaller than 1 times 10 to the negative 7, which is obviously 10 to the negative 11. 1 times 10 to the negative 11 is smaller than 1 times 10 to the negative 7, of course. Negative 11 is smaller than negative 7. And that means our pH level, though, because pH level is just a value, will be greater than 7 when we use the logarithm rules. That being said, thank you, grade 12s, for joining me this evening on yet another acids and bases lesson. What we covered in this section today, we covered the ionization of water, we looked at titration calculations, as well as the pH scale. Thank you so much for joining me, and I'll see you for the next session.